Hello and welcome. For our test experiment, we performed a quality control study on small-scale consumer wind turbine blades. We would like to begin by first thanking Professor Visser, Mark Hebel, and Professor Hoover for all of their help throughout the project. To start with a little background, for our experiment, we analyzed the 1.3 meter long wind turbine blades of a ducted wind turbine as shown in the top right image. The blades are made of aluminum and are pressed using the jig pictured in the bottom right. And the reason for our testing was because up to this point, the blades had not yet been tested for QNC. The key question being asked in our experiment is the quality and repeatability of the manufacturing method described on the previous slide. The significance of the experiment lies in the efficiency of the turbine. In preliminary testing, the average cost of power produced by ducted wind turbines is 7 cents per kilowatt hour, compared to the 24 cents per kilowatt hour of other small-scale wind turbines. Given that the blade geometry is directly related to the efficiency of the turbine, it is important to ensure a consistent blade is produced. The variables for our experiment are standard deviation, percent error, and variability of the geometry across the blade. Our parameters include the percent span, the percent chord, and the elevation of the blade. The control used for computation was the mean blade geometry, and the measurement method involved using a dial indicator and measuring tapes.
This is a brief overview of our schedule. On the 16th of February, we finalized our test proposal. Then on March 8th, we finalized and submitted our test plan. On March 14th, we met with Mark Hebel, and then on March 28th, we received the turbine blades from Professor Visser. On the 30th, we took a tour of Mark Hebel's workshop to observe the pressing machine. On April 1st, we prepared the blades for measurement, and then on the 17th, we completed the measurements. On April 21st, we completed our analysis. To begin our procedure, we first measured the span, the root chord length, and the tip chord length of all three blades. Next, we established a point of origin that was the same on all three blades. After that, we marked a line perpendicular to the chord length from the point of origin using a chalk line. We then marked a second line parallel to the first at an arbitrary distance away, also using a chalk line. On these chalk lines, we made marks at 4% spanwise intervals with pencil. We then connected these marks, extending them from the leading edge to the trailing edge, also with pencil. On these vertical lines, we made marks at 10% chordwise intervals. For the next part of our procedure, we situated the blades on a flat, level surface. We made sure to support the blade using machinist jacks, ensuring the point of origin was not elevated. All blades were supported in the same exact manner to ensure the best repeatability in our experiment. Using measuring tapes, we recorded the distance from the origin in the x and y directions to every point. Next, we used dial indicators to record the distance from the origin in the z direction for every point. For the third part of our procedure, we calculated the variation of each corresponding point between the three sample blades. We also calculated the standard deviation of each of the corresponding points, as well as the percent error between these points and the mean value.
The equipment used for this analysis process include a dial indicator, chalk line, square, and tape measure. The materials include the turbine blades and a laser table. The turbine blades were provided to us for free by the manufacturers Professor Visser and Mark Hebel. The laser table used as a level surface was provided to us by the Clarkson-Baja team. For the project, we bought the dial indicator for $41, the chalk line for $10, the square for $15, and the tape measure for $10. This totaled to $76 needed for the completion of this analysis project. For this project, there was minimal risk. The only potential source of risk came from possible jagged edges on the turbine blade. This risk was mitigated by sanding down of jagged edges by the manufacturer and use of safety equipment if necessary. The blades were all very lightweight, and the need for safety equipment was pretty unnecessary as the blades were very dull thanks to the manufacturer Mark Hebel. For the final results, we have the average variability and average percent error. The average variability is found between each of the blades in the X, Y, and Z direction. The average percent error is found between each blade and the mean value of each blade in the X, Y, and Z direction. To conclude, I'd like to show the maximum percent error in the Z, X, and Y direction. From the results, we can see that the most variance and error is found in the Z direction. The most likely cause for this large error compared to the other directions is the varied spring back during the manufacturing of the blades. The elevation of the blade would be most affected by the aluminum sheet trying to regain its shape. Though the method of measurement combined with human error can also have contributed to this large error. Every measurement in the Z direction was done by hand with a dial indicator. Throughout the calculations, the dial indicator was zeroed multiple times, and this can be a large source of error. While the outcome of this experiment was expected, if the experiment was to be repeated, we should use a laser measurement system to reduce the amount of human error contributed to the results. Lastly, we'd like to thank you for listening to our presentation, and again, thank Professor Visser, Mark Hebel, Professor Hoover, and the Clarkson-Baja team for their contributions to this project.